When looking closely at this simple rendering of a NURBS model, one can easily spot that something isn't set up properly. Everything looks terribly jagged. This can't be intended. In this clip, I'm going to talk about optimizing NURBS surface geometry so that it appears perfectly smooth in renderings. I'm primarily addressing users who are still quite new to rendering with Maxwell for Rhino, but also those users who prefer to create their geometry inside CAD applications other than Rhino and who bring their models in as NURBS surface data just for rendering. Have a look at these two simple NURBS surfaces. I'll now create a blend between them with the Blend Surface tool. In its dialog, I get all sorts of tweaking options offered, but I'll call this good enough for now. All I want to make sure is that I create a smooth transition. This should be the case with curvature continuity checked. When I now join these surfaces together and run the zebra analysis tool, one can see that the projected stripes match up and don't show any sharp kinks at all. We've just created some decent quality geometry. If these surfaces were now some detail of a part which gets physically produced, one would likely not run into problems downstream. Now let's apply a Maxwell material and start fire. Oops, look at that. Although the NURBS geometry is perfectly fine, the rendering looks just awfully coarse. The reason is quite simple. Render engines don't even see the NURBS surfaces. They work on a secondary layer of geometry, polygon meshes, which are also required to render the model in a shaded viewport. While these meshes normally aren't directly editable in Rhino, one can extract them. And here one can see how loose the mesh settings actually are. When one uses Rhino just for modeling, one may even forget about the existence of render meshes. Rhino creates them silently in the background, and for many users, one simply doesn't really have to care about them. But when it comes to rendering, one really needs to shift the focus. Whether a model appears rough or perfectly smooth in a rendering is up to the quality of the meshes, which represent your NURBS surface geometry. That doesn't make the role of the NURBS input less important. In the first example, we have already seen that there's great options to make a perfectly fine model appear a lot worse in renderings than it actually is, but the opposite doesn't work. So there's no way to improve the visual appearance of a poor NURBS model just by tweaking and spending a lot of time with the render mesh and making it very accurate. This model here has all lumpy geometry. Surfaces don't match up properly. One can already see that in shaded view, but it gets even more prominent in Zebra. It, however, has a very decent and precise render mesh. That doesn't help it really, does it? Of course, this has been quite an extreme example, but indeed the mesher will always pick up the NURBS topology. So if the NURBS consists of a single surface, the mesher will create a single mesh patch. Polysurface will spit out the mesh which has the same patch layout as the input surface geometry. If the polysurface is closed, your mesh will be again a solid mesh. If one has naked edges in the NURBS model, the resulting mesh will have gaps as well. Gaps in geometry may cause all sorts of problems, as render engines expect your models to be closed, and Maxwell is quite picky here. Problems don't get too obvious on simple diffuse materials, however. These three models here look quite identical in the viewport and also in fire, although eagle eyes might see some issues on the rightmost cube. What's wrong gets more prominently visible when render materials don't just reflect the light touching the surface, but also interact with the light in more complex ways. That could be glass or subsurface scattering materials. These materials absolutely need a clear definition of what's inside and what's outside, and of existing wall thickness. With open objects, this just can't work. Here's how the same scene looks with a translucent plastic material applied. The left one is fine, but the two others look somehow odd. Here's how things look after 10 minutes of rendering. Switching the Rhino viewport to shaded shows what's going on. The leftmost model is closed. The middle one is actually identical, I only have exploded it. On the model on the right, I also have moved a couple of faces slightly so that there's tiny gaps. When I simply join the middle one back together, it will render fine again. I'll now look at the initial model again and will try to give it a render mesh which matches the NURBS geometry closer and renders nicely. Before I start, however, I would like to briefly cover something one should not do, although it seems to be a quite often given advice. Please don't run the Rhino Rebuild command in order to refine the visual appearance of the model. When doing so, the instant result looks totally plausible, as seen here. I'm giving this cylindrical shape, which looks worst, a crazy subdivision, and the shape indeed changes, also in Fire. So what's wrong here? What's wrong here is that we are working on the wrong geometry type. Rebuild is a NURBS command. That way we are making the NURBS surface geometry, which was already perfectly fine, far more dense than it needs to be. If one introduces more complexity to the source geometry, the render mesh in most cases will somehow follow, more or less by accident and without any control. This action may ruin the model and make it a lot heavier without any need. If one repeats the same action many times in a file, one will quite likely run into performance problems. So what to do instead? One should leave the surface geometry alone and instead make the render mesh more dense. Here's how. Render mesh settings in Rhino are stored in templates. Typically, these are empty files which have a number of settings checked for a particular purpose. Small object millimeters, for example, is a widely used template, and here's explained what it's good for. Inside Tools Options, there's Document Properties and Mesh. Whatever we dial in here only applies to the current document, but when we save it to a template, it gets reusable. When one first opens this section, there's only two presets, one loose tessellation and one which is somewhat denser. Any of those two should actually have prevented the extreme display issues we saw in the beginning. Switching between the presets, one can see things change. But let's assume that I would like to use displacement on that part, and that my goal was to get rid of these long spiky triangles here. When checking the custom option, I now get a slider that lets me crank up the settings somewhat more, but it doesn't really help me with the triangles. So let's enter the detailed controls. This is an area which might appear a little bit intimidating, but it's not that bad really. Actually, these are the same options one also gets offered in the surface analysis tools and also when one exports a dense mesh, for instance, for 3D printing. We want to render, and in each of these cases one wants to get a mesh with quite different properties. That's why there's such fine-grained controls. The values seen here are pre-populated from the last used preset, but let's simply dial in 0 everywhere and let's check all boxes and also set the slider to 0. 0 in this case means please measure, just disregard this entry. At this stage, Rhino uses a generic minimum value so that one can see at least something in the shaded viewport. What each single of these parameters does exactly is explained nicely in the Rhino help file, but I'll give a few quick examples of the overall work principle. There are some settings in here which are scale independent, such as setting the maximum angle of mesh faces to the underlying surface. Another one is the minimum quad setting. In both cases, the meshing result on the large and on the small part is identical. And then there's other settings which take the physical size of models into account, such as the maximum edge length. It always works in the unit which is used in the template, in this case millimeter. What results in a pretty dense tessellation on the large part appears very loose on the small part. Things only get a little bit more complex as soon as one starts combining parameters. When I tell the software to approximate the NURBS surface so that the maximum distance between surface and mesh is less than a hundredth of a millimeter, the measure needs a lot of geometry in the fillet area, but it manages to be sufficiently accurate here on this bulged surface. Here it comes along with just a few long and spiky triangles. One of several possible ways to get rid of those would be to limit the allowed length of mesh faces. The more parameters are set, the more difficult it gets to track down what's going on. but for rendering with Maxwell, one actually doesn't need very nifty settings. There's no way to totally get rid of triangles on Rhino's real-time created meshes. They are simply the consequence of trimming holes and also of joining stuff with wildly different topology together. But one can make these triangles small. That way they will not cause problems in the image calculation. One important fact to keep in mind is that Maxwell doesn't require render meshes to be as small as somehow possible in terms of polygon count. A heavy mesh doesn't really affect the render time negatively. Only the initial export to the engine may take a little bit longer. That actually marks quite a big difference to other popular render engines for Rhino, where mesh size is absolutely critical for maximum performance. As there's simply no need to count every single polygon, I tend not to use these two settings when meshing for rendering with Maxwell. Both parameters are there to limit total polygon count through local density control. This, however, will likely introduce triangulation in the middle of the surface as seen here. The result may be more precise with less faces, but an evenly divided mesh would be a more suitable input for rendering displacement. With this super simple mesh setting and a custom mapping applied, one cannot see that this item is actually composed out of 3 different submeshes. What I just showed was the location where global mesh settings are stored. Any change here will affect the tessellation of every single object in the file. It's, however, not possible to set up some sort of one-size-fits-all tessellation setting, which will always work fine, regardless of the topology of parts you're working on. That's why Rhino also offers the same sort of controls on a per-object basis. They're found on the Object Properties page. That way, one can work with a loose global setting for a file with loads of boxy items, and only use denser settings for the few parts with more curvature. The same principle could also be used to cut down mesh density on background objects. Everything which appears small in the background doesn't need to be densely meshed. That way, one can make the scene export somewhat faster. If, however, those many parts are identical, it would probably be more effective to use instancing instead. But that's covered in another clip.